to be here. So I'm going to talk about topological K-theory, and I'm going to focus on complex K-theory. So there's not going to be any BO here. And I'm going to talk about, so in this lecture and then the lecture after lunch, I'm going to talk about the way that K-theory can be used to solve some problems about pretty concrete objects, vector bundles on spheres, division algebra structures on real vector spaces, and so on. And I think this really serves to illustrate one of the first big successes, big applications of generalized cohomology theories to sort of more classical problems. So let's talk about that. I guess that Dylan covered a little bit of what I'm going to say in his talk, but I'm going to start there anyways, and hopefully that's not too excruciating for you. But just let me know if it is. So first I'm going to talk about group completion. So the input is going to be an abelian monoid. So this is something with a commutative addition. It's associative, and it has a zero element. So it satisfies the usual things. It looks like an abelian group, but it doesn't have inverses, potentially. So what are some examples? Some examples include the non-negative integers. I guess some people would call this the natural numbers, but I usually call this numbers at least one. Is that weird? Okay, anyways. So another example would be the multiplicative, the positive integers. Positive integers with multiplication. So here, what do I mean by additive? I just mean that I'm going to write plus for the generic symbol. The fact that this is multiplication does not, I don't know, hopefully that's not confusing. And then another example is the any abelian group is an example. So what's wrong with these things like this? Well, they don't have inverses, and we kind of like inverses, maybe. It turns out that they simplify lots of problems. Monoids can be insane and horrible. Groups are nice, especially abelian ones. So we might want to have a way of turning an abelian monoid in a kind of universal way into an abelian group, and this is the process of group completion. So the definition, and I guess I'll explain. The group completion of M, this is assuming it exists, which it does, is an abelian group that I'm going to denote M inverse M, and I guess this is maybe not as common in algebraic topology, but it is very common in K-theory. Sorry if that causes confusion, but okay, it's an abelian group M inverse M together with a monoid map from M to M inverse M, such that, satisfying the following universal property, such that for any, I'll write it in a diagram form. If I have a map from M to an abelian group, I look at this map, then there's a unique, maybe this is better as a dotted arrow. So the universal property says whenever I have a map from M to an abelian group, it factors uniquely through this given map to M inverse M, and then a map from there to the abelian group. So if you think about what this means, is that this means that HOM in the category of abelian monoids from M to A, where I'm just going to view A as an abelian monoid, this is in bijection with HOM in abelian groups from M inverse M to A. Okay, So what this looks like is this looks like the value of Fm, where this is a left adjoint from the forgetful functor. So if I have an abelian group, so this is the category of abelian groups and homomorphisms, abelian and monoid homomorphisms, I can always forget, and there's a left adjoint to this. Okay, so this is a kind of categorical way of viewing what this operation is. Okay, and so if you prove the existence of this adjoint, then it gives you a functorial construction of f of m for all monoids m. Question? So the existence of f of m would imply that every monoid has a completion. And yes, this f exists. So I'll just say this, m inverse m exists. You can prove it either show that f exists, and you can do this using categorical nonsense in the adjoint functor theorem. I've left that as an exercise for tonight. So you can prove that exists, naturally. Or you can just write down a concrete presentation for it, and that's what Dylan did. So the second proof, take set this to be Fm mod Rm, and let me define what these are. Fm is going to be the free abelian group on the elements of M. So on generators, M, where M ranges over every element of M. Okay? So this is some large abelian group. Okay? If M is a finite monoid, it's, the rank is, well, in general, it has the cardinality of the monoid, just for the generators. And then Rm is the following, this is the subgroup. Okay. At some point, I'll start writing on another board, so this won't get infinitely bad. Generated by the following relations, it's so close. M plus n is equal to M plus n. Okay, so this forces the same monoid relation that holds because of the monoid structure of M to hold in this abelian group. But on the other hand, now we also have inverses because we have minus M is an inverse for M. So we've created. Okay, I'm done. I'm done. So we've created inverses by this process. Yeah. No. Because you're not creating multiplicative inverses. You can go maybe from the multiplicative ring of maybe a Dedekind domain to the multiplicative to the units in the quotient ring. Yeah. Okay. Let's talk about that later. Okay. So that's a proof that a sketch that exists. Two different arguments. Let's see. So that there are some exercises about some different presentations for this, which is helpful. Yeah. So now let's switch here. I'm going to write on as many boards as I can. So let's see. Let's return to our examples from earlier. What's the group completion of z more than or equal to 0? Z, good. What's the group completion of z more than 0 with this multiplicative structure? Positive rationals. And what's the group completion of an abelian group? Itself. Good. Okay. one more remark about this sort of general stuff is that if M has additional structure, oftentimes that structure passes to the group completion. So if M is a semi-ring, which means it satisfies all of the axioms of a ring except for of an associative ring with unit, except for the additive inverse, M is a ring with one, but possibly without additive inverses. What? Yeah, exactly. So if then M inverse M inherits the structure, can be given the structure of a ring, is a ring, and the map from M to M inverse M is a semi-ring homomorphism. Semi-ring map. Okay, so that's the common, and this will be used in the next slide. Okay, any questions? This is morsel 1. Okay. I guess I'm hungry. Okay, what is the monoid that we really care about? The monoid that we're going to care about for this talk, and really the monoid that everyone should care about in general, is the monoid of complex vector bundles on a space X. So this is the abelian monoid of isoclasses of finite dimensional, if that needs to be said. I guess that's usually part of the definition of a vector bundle. Finite dimensional, okay, I'm going to assume that X has finitely many components or something silly like that. Finite dimensional C vector bundles. So what is the sum? The sum is the direct sum of bundles, right? I have eta and psi, and I can take their direct sum. That gives me the monoid structure, and the tensor product of bundles makes this a semi-ring. And it's actually a commutative. I'm noticing a pattern here. Unfortunate pattern. It's a commutative semi-ring. Okay? So the definition, the definition is, I'm going to use slightly different notation just because I did so in my notes, so I'll forget at some point either way. KUX is going to be the group completion in this sense. Oh, did I call this something? Yeah, the group completion. Group completion of vect CX. And it's a commutative ring. So in other words, this is, in wordier, this is vect C inverse vect C. Okay, so the notation breaks down here, obviously. So let's think about a little bit. So this is the complex K-theory group, or the Grothendieck group of X. There's a Grothendieck group of complex vector bundles on X, or the complex K group of X. And you'll either see KU or just K unadorned. And just remarks, can do the same to vect R of X and get KO of X. So this is the monoid of real vector bundles. Or we can do this to the monoid of quaternionic vector bundles and get K symplectic of X. There's no tensor product here, so this one is just an abelian group. This one is another semi-ring, but I'm not going to use these in either of my talks. But those are the definitions if you want them. So let's unpack. I really want to write on the TV, just continuing to go. right here. Excuse me? Sorry, KOX is a ring kind of semi-ring. Sorry, yeah, it's a ring. K-symplectic X does not have is a multiplicative structure. That was the point I was hoping to make. So let's just unpack very briefly what kind of reassess what our definition of K-theory is using this description of the group completion. So, okay, I'll resist the temptation. So, okay. Questions while I'm erasing? Comments or, well, okay, maybe. Actually, only questions will be accepted until after the talk. So, okay. What's this one? So, okay, so let's unpack this. So Ku of X, in words, it's the free abelian group on isomorphism classes of vector bundles of eta with the imposed relations. So okay. Maybe let me take out phrase. So is the abelian group on isomorphism class of vector bundles subject to the relations that if I have that the eta plus psi is equal to the eta plus psi. Okay, I don't know if this was helpful, but hopefully it was. So this is just this definition, this presentation for the group completion applied to this particular monoid. So the elements of KUX can all be represented by formal sums of vector bundles, and we have this rule that we can combine, we can kind of split them up in this way. Okay, so this tells us how to compute in this ring. Okay. Well, I mean, one might call them virtual vector bundles. That's all I got at the moment. I'll try to think about it more. It's a formal operation. We're doing something somewhat formal. And let me say why we might want to do this before I move on. K-theory is awesome, and vector bundles are very hard. So if I gave you some topological space, even a relatively simple one, like, I don't know, S5, and I asked you to classify all rank 2 complex vector bundles on that. Well, you can do it. There are exactly 2 isomorphism classes of such bundles. But it requires the hard part of Bott periodicity. It requires the first unstable homotopy group of U2, the second unitary group. So this remark, pi 5 BU2 is Z mod 2. What this exactly means, right? This is, what is this? This is maps from S5 to BU2. And I don't need to worry about a base point because this is connected and simply connected even. So this means that there are 2 rank 2 bundles on S5. How would you have ever guessed this? These bundles, do you know what Chern classes are? Some of you probably do, some of you probably don't. All of their Chern classes vanish, right? Because there can be 2 Chern classes, one in degree 2, one in degree 4. The cohomology of S5 vanishes in those degrees. So there's no way you can understand these bundles. You have to be Bott, I guess. K-theory takes this kind of chaos at the boundary of Bott periodicity and sort of deletes it. And on the one hand, that means it loses information. And you can see that because we're doing this formal thing. We're doing something formal, so we're probably not going to capture the kind of rich geometry in the original problem of understanding vector bundles. But on the other hand, what we're going to see is that it makes things be very computable. This is kind of a non-abelian problem. That's part of the hard aspect of this problem. This is coincidentally a group, but there's no natural group structure on rank 2 vector bundles on S5. Okay, so, okay. Okay, I'm going to take a breath for a moment. Okay. Any other questions? Okay, so so a lot of this talk is going to be generalities about K-theory, and then the next talk will be some computations that are pretty neat. Right, so I wrote a couple problems based on this for classifying rank 2 bundles on CW complexes up to dimension 6. And so we can talk about that afterwards. So the general way to do this is to study the Postnikov tower of BU2. I mean, you can do it in two ways. You can kind of filter the source, write it as a CW complex, and kind of extend over the skeleton. Or you can kind of co-filter the target and write down a Postnikov tower and try to lift maps up that tower. I'm not going to say a lot about that, though I would love to. It's just it won't get me where I want to go right now. But during the problem session, we could definitely discuss how that works, and I'd like to, because it will really tell you, like, shit, K-theory is a lot easier. Okay, so reduced K-theory. So let's say XX is a based space. And I'm really not going to worry about, all of my spaces are as nice as possible. I'm not going to stress about any point set theoretic issues. So then I'm going to define KU. Okay, this is completely obvious, but I didn't say it. Okay, other remark. KU blank is a functor on, I don't know, whatever. I don't know. For me, everything's a CW complex, but on top. KU tilde X, and I'll either include the notation or I won't include the notation. This is, by definition, the kernel of the kind of restrict to your base point map. Okay. So this is the reduced K theory, reduced complex K theory. There are no stars. Oh, yeah, exactly. It's either X or star. It's. Oh, yeah, right, exactly. The base point. However, yeah. Okay, so this is the reduced K-theory group. Now, this group, if you think about it, okay, so let me come back to this after some examples. So first of all, KU of star, a single point. What is this? Why? Someone? Right, because a vector bundle on a point is just a complex vector space, a finite dimension. And so so the monoid that we're doing is the monoid z more than or equal to 0. So we're group completing that monoid, and we already discussed that was isomorphic to z. What is this isomorphism? This is just the rank isomorphism. This is induced from just picking out the rank of a vector bundle. So this map, what we're doing is we're measuring the rank at our chosen base point. And that rank might be positive or negative. We compute it by I said that any class here is a formal sum of vector bundles. And so we just take it by taking that formal sum, but then inserting the rank of each vector bundle that appears. Okay, so this is an easy one. What is the reduced K-theory of a point? Yes, question.
Which way do the arrows go?
Right, it's okay, op. Thank you.
So we're using the base point map.
We're using the base point map. Exactly. So in fact, for a pointed space, there's a canonical Z summand of KU. So I'll write that down in just a moment. Good. So what is this? 0, good. And yeah, so in general, we have our map X. Well, okay, I'll write star, and this sends a sort of abstract point to X, and then there's always a canonical map from X to a point, and so this provides a canonical splitting for KU X isomorphic to KU tilde X, the reduced K theory, plus the integers. So this is canonical for base spaces. Okay? In general, only this map, only the map from Z to KU of X is canonical for arbitrary spaces. And that's just the map that sends n, the number n, to the free rank n vector bundle on X, the trivial rank n vector bundle on X. Okay. So this, So just as a kind of, so I want to, this is not a precise statement, but the way I think of this is as the Grothendieck group of rank 0 virtual vector bundles on X. And this rank 0 means at X. Okay? If X has multiple components, this reduced K group is a little bit weird because we basically, we're not changing anything on the components that don't contain the base point. Okay? So those components have K classes that have whatever rank. Okay? But in terms of this particular choice of base point, it looks like those things have rank 0. Okay, so it's a little weird to consider reduced K theory of non-connected spaces, but anyways, but it's something that exists. Okay, so and then a lemma that's easy to prove. So I started at something 40 and I go to when? Okay.
You get what I mean?
I see. Understood. I'll try to stop early instead, just for a change of pace. Yeah. I think we're doing well here. Okay. So lemma. I wanted to give a different presentation, one that doesn't pass through K theory, through this group completion for the reduced K theory. So if X comma X is a connected nice space, what else do I really want to say? Oh, yeah, I do want to say this. Compact Hausdorff space, or finite CW complex, or something like that. Then I can compute KU of X in a different way as the set of equivalence classes of complex vector bundles for the equivalence relation tilde, where eta is equivalent to psi if and only if I can add, if and only if they're stably isomorphic. So I can add a trivial rank n sum n to one, a trivial rank n sum n to the other, and they become isomorphic. So what this means is stably isomorphic. They're not necessarily isomorphic. They don't even have to have the same rank, if you look at this. They don't have to have the same rank. Oh, by the way, as you've noticed by now, blackboard 1 to something is the trivial rank n bundle on whatever space we're looking at. Okay? So we're saying that two things are equivalent, two vector bundles are equivalent if for some m and n, they're isomorphic. And, yeah. And once it's true for one pair, it'll be true for a bunch of pairs, right? It'll be true for m plus 1, and so on and so forth. Okay. So the proof is very easy. Let's consider the map from vect xc to ku tilde x, reduced K theory, that sends an isomorphism class eta to eta minus 1 to the rank eta. Maybe I'm overdoing it with these isomorphism classes. So first of all, let's test, is this actually a reduced K class? Or let me ask a smarter question. Why is this a reduced K class? Okay, true. Why is it the kernel of some K theory? It has rank 0. The rank of this is rank eta. The rank of this is also rank eta by choice, exactly. And now I claim that this map factors through this equivalence relation. You know, what I don't. Okay, so what I need to show is that if these are the same, then the classes that they go to are the same. Okay, so now I'm going to have eta. Let's see, what do I want to say? So what am I supposed to show here? So if right, I want to show if these are the same, then these are the same here, I guess. Okay. So so of course eta plus 1 to the m is equal to psi plus 1 to the n. And now let's see. I don't think so. Not for this step. I think that's for the next step. But no, this is. So what do you have in mind? And then what? I don't. Okay, so do people know what he means by the inverse bundle? Is that something that came up? Okay, so let me make a remark about that, and then we'll see how it's useful. So one reason why compact Hausdorff is required to prove this theorem is to show that this, one consequence of this lemma is that this is already an abelian group. And in particular, that means that every bundle is going to have an inverse with respect to this equivalence relation. Okay, what that's going to mean, so notice modulo this equivalence relation, all trivial bundles are 0. Okay, so in vect Cx mod tilde, 1 to the n is equal to 0, because it's an example of this equivalence relation. Okay, where m is 0 and n is n. Okay, so what does it mean to be an inverse? I need to have psi plus some other class psi to be equal to 1 to the n. Okay, and then if this occurs, then psi is a kind of inverse for this. Okay, and so and of course this is the class of eta plus psi. Okay, so a psi such that eta plus psi is 0 is an inverse for eta, and these always exist on compact Hausdorff. So eta inverse such that eta plus eta inverse is trivial always exists when x is nice in this form. X is compact Hausdorff. Let's see. So that's the reason for this. The reason for this is basically these infinite Grassmannians. Since x is compact Hausdorff, it actually maps to a finite Grassmannian. So eta is basically a map from x to the Grassmannian of k-planes in some large complex vector bundle. That's what the compactness gets you. It lets you go from the infinite Grassmannian of k-planes in kind of C infinity, and says the compactness tells you that factors through a single finite stage. Okay? And once you know this, once you put a Hermitian metric on Cn, there's a canonical orthogonal vector bundle, and that is eta inverse, because eta plus eta inverse is C to the n, and that's the trivial vector bundle on this Grassmannian. Okay, sorry I said that out loud instead of writing it. I wasn't prepared for that, so that was kind of winged. Any questions about that? So this is a pretty important point.
X and manifold, you've seen it before. Manifold divided by 30.
You've seen that for the special case of the tangent bundle. Exactly. So, okay, and now for some reason there are just too many things up here. So I guess the suggestion from Peter was that I add to both sides of this equation. So I'm going to add eta inverse plus eta, and then I'm going to add a psi inverse, and then this is 1 to the m, and this is isomorphic to psi inverse. Just one of the inverses, but then I don't. Okay, I'm just going to trust you. I don't see it yet. The board is too close to me, exactly. So then this, of course, this is trivial. So then now I'm in a like 1 to the r plus 1 to the m, and this is isomorphic to whatever this is. And what was I supposed to prove? Oops. And now, that looks, this, yes. What? Why? Oh, the left side.
Yeah, left side.
Oh, the left side goes to 0 here. Ah, thank you. Good. Okay. This maps to 0 via the map that I just described to you. And this maps to whatever it maps to. So So I guess we're done. Everyone sees it but me, so okay. Sorry. I trust you. So this shows that we get such a map, and that this factors through, so, so this means that we get a factorization of vect c x mod tilde to ku reduced x. And so then the last part is to show that it's surjective and that nothing else can go to 0. And this follows from exercise 8. So conclude by exercise, by problem 8. 4.8, 4 for today, dot 8. So it's pretty easy to see how this goes, but I'm not going to try to mess around with these equivalence classes anymore. We saw what happened there. So, okay, that's good. What's nice about this is it doesn't appeal to this kind of magical group completion thing. It just is an equivalence relation on a single monoid, on a single set. And you'll note in this presentation of reduced K theory, this is a group, and the sum is really just induced from the sum on the monoid to begin with. Okay, so. Okay, so now let me, I guess maybe this was already, was this really proved, or was it, well, you'll tell me. So theorem, X compact Hausdorff. Then Ku of X is isomorphic to the set of homotopy classes from X to Z cross BU. And the reduced K theory of X is isomorphic to the set of based homotopy classes from Z to BU. Now, this is kind of dumb to say it this way, but this is my preferred way anyways, for reasons I guess I'm going to keep to myself. So what's the base point for here? I'm going to point this by the component 0 cross BU. Okay? And so that means that this is, this is the same as maps from X to just BU. Pointed maps from X to BU, because why mess around with the other components? You know you're not going to work with them anyways. And then this, I was a little disturbed by something you said, but I believe this is just X to BU in this case, since BU is simply connected. The points, I can always move any map inside BU in some sense. Yeah. For this, I'm gonna point it, or I could add a disjoint base point. Thanks, though. Yeah, here I mean X pointed. So, okay. So the theorem is just saying that in some sense that this group, which is this kind of mysterious group completion, is representable. Okay. So the motto. And this will really take you far in life, as it turns out, is that K theory is representable. Here in Okay. So when X isn't compact Hausdorff, this has better formal properties than this. Okay. But that's not going to really worry me today. Okay. So, okay, let's continue.
Maybe it's worth emphasizing that usually for
Right, that's what I guess I'm trying to say, right? That if you have to choose in cases where this is not an isomorphism, you want to choose this side, as it turns out. So that's a general. Any cohomology theory is determined by its values on compact Hausdorff spaces. And there's a kind of formal way of extending it to arbitrary spaces. And when you do that, you get this definition and not this definition. So let's prove this. Was this already actually proved in the lectures? No, just remarked.
There's the XBUN calculates N.
Right, okay. So yeah? Right, vector bundles were shown to be representable.
Yes.
But not this.
Real case, so, but
Okay.
we've got mine,
You
but
thought it.
same thing.
Yeah.
Yeah, but that's it, yeah.
I just prefer C.
We told them that this would happen.
Yeah, exactly. So, okay, what's the proof? So the proof is that I'm going to use this lemma. Okay, so I'm going to right. So let's see. We can assume that X is connected because basically if we prove these for each connected component, then we'll have proved them in general, right? Because, okay. So we can assume that X is connected. And then it's enough to prove the second one because the first one is just a sum of the second one plus Z. Okay? So enough to prove the reduced statement. Never prove two results when one will do. So then there's a natural monoid map from vect C of X to homotopy classes of maps from X to BU. What is this map? Do I have time to be this leisurely? Yeah, why not? Okay, think of a map that takes a vector bundle on X and spits out a homotopy class of maps from X to BU. Yes?
Then the point on, so for your vector bundle,
Eta.
yeah. You send the point in the base to
Okay, good. That's more detail than I was hoping for. So I think what you're saying, can anyone rephrase that? Yes. Oh, yeah, let's take the classifying map. Okay, that's all, might be also true, or UN maybe. Let's take Eta's classified by a map from X to BUN. So I'll call this Eta N to denote its rank. So there's a classifying map from X to BUN that I'm also going to call Eta, because why not? And now what? Include into BU. Okay. And now if you think about this, because of how the direct sum works, if you have two of these, then it's compatible with how you define the monoids, the H-space structure on BU. The H-space structure on BU is built to encode the Whitney sum. Okay, so this is a monoid map. So what do we have to prove the theorem now? Now we have to prove, one, that it respects this equivalence relation and doesn't send anything else to 0, and that it's surjective. Sorry, the speakers are buzzing. Okay, so we have this kind of injectivity and so forth. So the first thing is that the compactness itself implies surjectivity. Indeed, what is the point? What is the key thing that compactness gives us? Well, BU is the colimit of the maps from the BUNs. And what this means is that the colimit of X to BUN, so there's a natural, let's see, is this the right way? There's a natural map from this colimit to this, and the compactness of X tells us that this map is, that this is a bijection. X compact. Okay. You can kind of see this very naturally when you take the particular Grassmannian, like doubly infinite Grassmannian sort of approach to this. But okay, so we get surjectivity done. Why? Well, okay, first take my map, take my homotopy class of maps here. Well, I can lift it to a finite level, but this X to BUN, what does it do? It classifies a vector bundle, eta. So what? Right, by pulling back the universal bundle, if you will. Mm-hmm. Okay, so that gives us surjectivity, no problem. So let's see, the other part, let's think about when two bundles go to the same class. Eta and psi map to the same class in X cross BU. So when does this happen? When? Okay, this is kind of, so I have X to BU, let's see, M and N, BU, M. This is the eta. I have X to psi, N, oh, sorry, BUN. That's classifying psi. And what am I saying? I'm saying that they map to the same class here. So in since I'm up to homotopy, I get a commutative diagram like this. These are the natural inclusion maps. Okay? So what does this mean? This means that in some sense, when I add an infinite rank bundle to eta and an infinite rank bundle to psi, I get the same thing. But X is compact again, so this actually, these equalize at some finite stage. So let's see how to say this. So yeah, BUN like this. Okay? So this, again, the fact that this happens uses compactness again. So we can do this at the finite stage. But the fact that this equalizes this, what does this really mean? I added a trivial bundle to eta, a trivial bundle to psi, and I got isomorphic bundles. Okay? So, eta and psi map to the same homotopy class of maps, elements of X to BU, if and only if I can add eta plus some trivial bundle and get psi plus some trivial bundle. But that's exactly this equivalence relation. Okay? So I see particularly, basically, that the image of KU tilde of vect CX in here is just KU tilde X, and it encompasses everything by this. Okay? So that completes the proof of that. This proves injectivity, right? Because we're saying that the only relations that hold in this set are the relations that we imposed and found by this lemma to give us reduced K-theory. So this shows it shows two things at once. One, it shows that those relations hold so that this map factors through reduced K-theory, but it also at the same time shows, because of the if and only if, that no other relations hold either because of the compactness. So there would always be this map, compactness or not. Oh wait, is that, yeah, exactly. But compactness gives us surjectivity and injectivity. Not necessarily. It's just in general, if X is finite CW complex, you just need to make the bundles, well, let's for sure make them at least twice the dimension, but actually you can probably add a dim X bundle to, oh, I don't know, I'm not sure there's a simple formula, but you don't have to add too much. Oh God. M prime and N prime. Sorry, my mistake. That was indeed confusing. Okay. Okay, so now we've seen, now we've seen representability of K-theory. This doesn't require Bott periodicity. I want to note that. There's no Bott periodicity in here. That's because this is all formal. We haven't done any computations yet. This is just some general stuff. Bott periodicity comes in when you want to actually compute some stuff. Or, Yeah. Okay. So now we're going to view K-theory as a cohomology theory, and I want to make a few remarks about this very briefly. So now I'm going to redefine for any X, KU0 of X is going to be defined to be homotopy classes of maps from X to Z cross BU. Sorry. And KU reduced K-theory in degree 0 of X is going to be pointed maps when this is a pointed space from X to BU. Or wait, what? Sorry, I don't know why I did this. This. What? I don't see why. No, this brackets now no longer mean space maps. But I don't think it matters. But I can if you want. I mean, I'm just claiming that they're the same. Okay. So now what I'm going to do is extend this definition in a standard way, and define KU to the minus n of X to be homotopy classes of maps from the suspension of n, from the nth suspension of X to actually what I really wanted to do was write this, and I'm just going to keep doing that. Okay, so for n at least 0, I'm going to make this definition for the reduced K-theory. Okay. Here it's unbased maps. Here it's based maps. There's not a huge difference. Basically, this contains some summand of a number of copies of Z's in it, corresponding to the. No, sorry. These differ by a copy of Z. So they're very close, but it takes slightly less work to define a reduced cohomology theory. So I wanted to define a reduced cohomology theory. Okay, so now I'm going to make an observation So what is KU? And now we start to see some fun. So what is KU minus n? Isomorphic to. Right, so on the one hand, right, that's good. On the one hand, this is KU 0 of the n-fold suspension of x. There's also a standard adjunction I could play around with here. What does that standard adjunction say? This is isomorphic to the homotopy classes of maps from X to the based loop space, the n-fold based loop space. And I'm being horrible here. I mean, this Z is not contributing very much to our discussion. And I'm not sure why I want to do that. It just feels good to me at the moment. So note that this is equivalent to loops n of BU if n is at least 1. Okay. Yeah, exactly. It'll seem a little bit more clear then. But anyway, so I can play this game. Well, now look, what seems relevant at this point? Bot periodicity seems extremely relevant. So let's play the following game. Okay, we don't have to play on that small of a playground. I guess I'm taking the plus 10 option, it looks like. Well, that's to court 10 till, right? Okay. So let's play the following game. I'm going to do K. So here n is going to be bigger than or equal to 0. And I'm going to do KU minus n minus 2 of x. Okay, so this is even more negative. So this is like if n is 5, this is KU minus 7. Okay. So I can write this as maps from the n plus second suspension of x to z cross BU, pointed. And now I'm going to split things up. Okay, I'm not going to do all of the adjunction at once. And instead, I'm going to do only part of the adjunction. Excuse me? BU is complex. Yes, U for unitary. So what is this space? Z cross BU. So what I'm finding, it looks like what I'm finding here is that this is KU minus n of x. Okay? So I get this periodicity phenomena. Every even negative K group is they're all isomorphic, and all of the odd negative K groups are also isomorphic. Okay? So what I'm going to do now is define KU tilde x. And I'm carrying around but suppressing a base point everywhere. I hope that's acceptable to you. N, I'm going to let this be KU minus the absolute value of n of x. Okay. This now defines K groups for all integers, not just the negative integers or the non-positive integers. It's for all integers now, and it's given by this formula. Now, this isn't necessarily all you need for a cohomology theory, but and the theorem, and the point is the real point. So the point, if you want to compute all of these groups, all of KU star x, it's enough to compute KU0x, which for nice x has this not algebraic, but this kind of concrete description, and KU tilde minus 1 of x. Okay, now this maybe looks a little bit more exotic, but this is also given by a nice construction. This is isomorphic to the complex K-theory of the suspension of X. Okay? So we can really potentially compute all of these things using kind of these down-to-earth descriptions. So this is vector bundles on X mod that equivalence relation. This is also vector bundles, but this time on the suspension of X mod that equivalence relation. Okay. The reason for defining these negative K groups is kind of just like, I don't know if people know what take cohomology is. That's probably less likely. Okay, sorry. It's just prettier this way. It looks symmetric in both directions instead of mysteriously stopping in degree 0. So for now, that's good enough. Okay, in the remaining minute or so, okay, this is actually pretty reasonable. Okay, and now the theorem is that this defines a reduced cohomology theory. And I'll say exactly what that means, or not, well, I'll say somewhat what that means. Ku tilde star is a reduced cohomology theory on pointed spaces. Oh, was this tops? Maybe this should be top star. I think that's what I chose earlier. Okay. So what does it mean to be, okay, and now let me give a remark. We can define an unreduced theory by defining Ku star of X comma A, where A is, now I don't know. Let's imagine these are CW complexes and A is a subcomplex, to be Ku star, the reduced K theory of X mod A at A, basically. So I've collapsed A to a point, so this is the base point I'm choosing. Okay. So this defines this is an unreduced cohomology theory, and there's a standard and formal way of passing back and forth between reduced and unreduced cohomology theories. This gives us the reduced to unreduced way. Okay. So, right, exactly. Mm-hmm. And let me just tell you the consequences, and we'll use these in the next lecture. So consequences of it being a reduced cohomology theory, just to keep in mind. So the first and probably most important one for us is that if A inside X is a CW pair, so this means that X is a CW complex and A is a subcomplex. Has that been discussed, these things? Okay, good. Then I get a long exact sequence in K groups. Then I get, in reduced K groups, I get Ku, I don't know, N of X mod A to Ku N of X to Ku N of A. I'm going to go around the corner, Ku N plus 1 of X mod A. And I'm going to keep going longer than is usually appropriate. Of course, I'm also going to confuse myself by doing that. And now where would this go? This would go to Ku N plus 2 of X mod A. But what just happened? It's a circle. Exactly. Well, yeah, that's right. Exactly. Okay. So that's consequence 1, and this is going to be the most important one for talking about the Hopf invariant 1 problem, which we're going to do after lunch. Really quickly, it's homotopy invariant. So these aren't consequences. These are really what you have to prove to make sense of this. Maybe I should say that in a different way. Consequences / what you prove to get the theorem. So this is what, being able to connect this loop is what Bott periodicity lets you do. And so that's kind of the cool thing about adding these negative K groups, which I think we like circles, so maybe that's compelling enough. Oh, and then just the last thing is that there are sort of, kind of canonical or up to homotopy isomorphism, suspension isomorphisms. Okay. So 2 we'll use implicitly all the time. It just says, yeah. Okay. I wanted to give some examples. I'll give them in the next lecture. Okay. Thank you.